we discussed earlier that the total area underneath any normal distribution, certainly the standard normal as well, is going to be 1. And I tried to give a little bit of intuition for how, if you take segments in terms of frequency polygons, or relative frequency polygons to be more specific, you can think about the area underneath a distribution curve from some part to another as giving you some information about the probability associated to that range of values. And I'll say that this stuff is one of the fundamental results of calculus, but it's also not particularly obvious. Understanding that accumulations are described by areas underneath curves is the sort of thing that takes more time than a couple of 2-minute videos to really understand. For us, we're not going to see every single detail, certainly not in terms of the calculus, but we should understand roughly that when we're talking about the areas underneath normal curves, we're really talking about probabilities associated to certain values. And in terms of computing this, the nice thing about the standard normal distribution, like I said, is it's a fixed pattern that we know a lot about. So if we want to find probabilities associated to it, if we want to find areas underneath, we actually just know a lot of the values. And we use tables to find them, or at least we can. I personally don't like that method a great deal, and it's probably my biggest frustration with the book, that the book assumes you should do it that way. I just disagree. But that's one way that we can think about it, where another way that we can think about it is in terms of the calculator using the cumulative distribution function, the cumulative density function for the normal distribution, normal CDF. So as I said, the vast majority of the work we're going to be doing here is going to be in terms of finding areas underneath the distribution curve for some region. And as a result, since we're accumulating things, this is mostly going to be done with normal CDF, or if you prefer Excel, the normal distribution function, or if you prefer the table, but it's not my preference. Anyway, we're going to be seeing quite a few examples over the next couple of sections, but let's start with a couple of basic ones here. So for our first example, we want to find the cumulative area that corresponds to a z-score of 1.15. Now, with this sort of question, it's important to understand exactly what's being asked, because when we talk about cumulative areas, when we talk about cumulative distribution values, we're talking about accumulation up to a point, not usually beyond, and not usually between. We're talking about up to, when we just say the word cumulative like that. So in terms of the overall distribution behavior, excusing the fact that I'm telling you the answer here when you see this picture, we're talking about the area to the left of that value, z equals 1.15. We're trying to describe that whole window of things that we have, where technically speaking, this value, it's from 1.15, it trails off into that tail, and it keeps going and 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 going forever and ever. Although, because it gets very close to the axis, most of those values don't do a whole lot for us, but it does technically keep going and going. Anyway, if we want to find that, there are a couple ways we can go about it. Either we can use the table, because it's a well-known value, where we go down to the row for z equals 1.1 and then find the column for 1.15 to get the cumulative area up to that point. But I'm not crazy about this because, for one, it's just inefficient to spend all that time table reading, and two, I don't like using something that is very explicitly discrete to talk about something that is by definition continuous. It just feels wrong to me. Besides the fact that it really limits your options as well. So usually what I prefer you do is handle this stuff in the calculator, where you'll see in another video detailed steps for how you can handle this, and I also talked a little bit about what that would look like in the notes as well. But essentially, what you would do in there is punch in the input normal CDF, -1 E99, 1.15, 0, 1, where this -1 E99 is what's called your lower boundary or lower bound. That is, it's the lowest value in the range that you're willing to consider, where because we're technically going off to infinity, we just make it a really large negative number. That's -1 followed by 99 zeros. It's really, really, really big and really, really, really negative. And then up here, we have our upper bound. So that's what we're going up to. Here it's 1.15. Then in that third value, we have our mean mu and our standard deviation sigma, where because this is standard normal, mu is 0 and sigma is equal to 1. But this is a general flavor of the kind of problem we look at, where to get the area, usually it helps to have some kind of picture here that we can work with, some kind of picture that we can understand and make our interpretation based on, and then put it in the calculator where it's a matter of learning the syntax. Let's get one more example though.